All right, it's 8:30, so let's go ahead and get started today. Question. For learning objective 3, control volume. CV is control volume. Yeah, CV is always control volume. Good morning, everybody. How's everybody doing today?
Usual, just waking up.
Good. Yeah. Can you believe it? We're almost halfway through the semester, so it's been by the end of the day it's been 7 weeks like this. So we're really making progress. I think once you hit the midway point, I think that's when it starts to hit you that it's the semester is going really fast. And so I'm done grading your midterm, so you guys should be able to see your scores. One thing I want to ask is that basically when I'm grading it within Canvas, it allows me to leave comments on each individual question. So have people been able to look at their midterms and then be able to see those additional comments per question? Because if you got the question all right, I didn't leave any comments on it, but if I took some points off, I left a comment basically kind of explaining why I took some points off and some feedback on that. So is everyone able to kind of view those comments okay?
I was able to view the entire exam, but not individual questions, if that makes any sense. I can click on grades, and then I can click on midterm 1. I can't see individual stuff. It says our answers are hidden.
Okay.
But there is when I do click on midterm 1 or whatever, there is a little comment section on the right-hand side that does show me your comment. And I missed it the first time through, but then I realized, wait, usually you can do comments and stuff. So I went back to check, and sure enough, it was there on the side. So
okay.
While I couldn't see individual questions, I could see that there was a comment left.
Okay. Okay, that's
could be a setting on Canvas that after grading, certain things can be visible or something. I know that was how there was a setting like that on Titanium last year or whatever. Canvas might have a similar.
Okay. Yeah, that's kind of. I wish it wasn't like that, because I left a lot of comments on those for each individual question. So the fact that it's not showing you guys is really disappointing. So I'll have to see if there's a way if I can get those to you, because that's where I basically left all my feedback on the exam. So right now all you guys can see is just the score of the exam and just kind of the overall comments on the right. Okay. Okay. So I need to figure out a way. So I might just go in and okay. Okay, so I might just go in and just kind of manually email you guys all the comments. Okay. Yeah, so I might go in sometime later today and email you guys all the comments that I left on each question, because it's that's probably the most important thing that I want you guys to get is those comments, because whenever I always try my best, and whenever I take off points, I try to kind of explain kind of why that is. So I'll make sure to get those comments to you guys, because I can still see them on my end, but I'm hoping that there's just a setting that I can do to make it visible to you. But if not, then I'll just email all of them to you guys. Okay. Okay. So let's talk statistics. So you guys did really well on the exam. So the average was 43.5 out of 50. Okay. All right. So you guys did really, really well, right? And so yeah, some people got 100%. So there were some people that did that, but otherwise the average was really high. So yeah, really happy with how you guys did on the exam. Any questions about? I mean, besides the comments thing, are there just any questions about the exam that I can answer?
Yeah, that last problem.
Mm-hmm.
No matter how hard I tried, I just kept getting a negative value. And
yes, I want to address that, because it's Brandon here. Yeah, Brandon's in the room. So Brandon kind of asked me several times about that question too, and I told him that the problem was fine. But then when I was grading it, I was looking over my solutions, and I found out that I'd forgotten to include gravity in that one. So it threw my numbers completely off. So I was getting a positive answer, but basically everyone was getting a negative answer. So once I realized that, I basically gave everyone just full credit for that part of the problem. So I know Brandon's probably feeling very vindicated right now, because he asked me so many times, like 2 or 3 times during the exam. So I apologize for that. That was my mistake. But for everyone that filled out that problem and you presented some work that made sense and you got a negative number, I gave you basically full credit for that. So that was my bad. And I should have caught that when I was writing the exam before. But yeah, with the numbers the way that they were, you get a negative number of balloons on that. So which makes no sense at all. So I apologize for that. And I'll try to catch that for the future. But I basically gave everyone full credit for that because that was my mistake. Yeah. Okay. Okay. So that's everything about the exam. So the plan for today, moving forward, is we're going to continue on with our lecture notes for control volume. So on Monday we did conservation of mass, and so today we're going to do conservation of linear momentum. Okay. And so it's kind of the sequel for this. Okay. But before we get started, I do want to clarify kind of one point that I made at the end of lecture on Monday that I said, which doesn't really make now that I thought about it again, it doesn't make that much sense. So I want to make sure I clarify this, especially once we get into momentum. Things are going to get confusing with all the different velocities. Okay? So if you recall, at the end of the lecture on Monday, we were talking about moving control volume problems. Okay, and then remember, for moving control volumes, in the inflow outflow term, we had something that looks like this, right? Okay. So this is basically our inflow outflow term from Reynolds transport with the adjustment for moving control volumes. Okay. So remember, this U right here, this is the fluid velocity. Okay. And since we have a moving control volume, this VCV right here, this is the velocity of the control volume. Okay. And so I think what I said at the end of class on Monday was that the fluid velocity, the sign convention for this only respects whether it's an inflow outflow. And so whether this velocity is positive or negative only depends on if it's, it's at an inflow or outflow. Okay. While this velocity right here, the sign convention that you use for this is the typical, if it's going to the right, it's positive, going to the left, it's negative. So this is Cartesian sign convention. Okay. So that's what I said. But it's actually, it was actually incorrect. And so the part that's incorrect is actually this one right here. So this velocity also actually respects the Cartesian sign convention. Okay. And so for that velocity, basically you're going to plug in a positive value if it's going to the right and a negative value if it's going to the left. But if it's a vertical flow, positive is up, negative is down. But the thing that that specifies whether this this whole thing is positive or negative is actually this entire thing right here. And so this sum right here, or this this product, just by taking the dot product with this n, this whole thing will have a sign convention of either positive or negative depending on if it's inflow outflow. So that entire quantity right there follows the inflow outflow sign convention. Okay. And so remember, for that sign convention, if it's an outflow, then that whole quantity is going to be positive. But if it's inflow, then that whole quantity is going to be negative. Or it's more like you kind of you switch the signs for this depending on that. Okay. And so I want to make sure I clarify that because that's once we start getting into momentum where we're going to have an additional velocity there. So we're going to have a velocity times a velocity. These sign conventions are going to be extremely important just to make sure that you get your forces and your quantities going in the right direction. So and so I want to make sure you do that. So inside the parentheses, everything follows just the regular Cartesian sign convention. But once you make the dot product with this normal vector, then you follow the inflow outflow sign convention. Okay. Okay. Any questions on this? I know it's a little bit kind of abstract right now, but once we start doing some momentum problems, I think it'll start to make a little bit more sense.
So it's,
yes.
Oh, I'm sorry.
Oh yeah. So question in the chat. So inflow is negative and outflow is positive. That's right. Yep.
So it's only the inflow outflow sign convention when the entire dot product is either positive or negative.
Exactly, right. So once you make that dot product, then it'll make the thing either positive or negative. Or it's more like you make everything the same sign if it's an outflow, or you switch the sign if it's an inflow.
Okay.
Okay. Okay, so then now let's move on to conservation of momentum, or more specifically, conservation of linear momentum. Okay. And so we're going to follow the same process that we did for conservation of mass, where we're going to start with Reynolds transport, and then we're going to apply, we're going to plug in our expression for momentum. Okay? But before we do that, I just want to talk about just conservation of linear momentum just in general. Okay? So basically how you understand momentum from your physics classes. Okay? And the way I kind of want to summarize it is, I want to think about how can we change the momentum of an object. And so what I want to do is I want to express the conservation of momentum like this. And this is basically Newton's second law. Okay? So I'll call that M2. Okay? And so what Newton's second law says is that the time rate of change of linear momentum of an object, okay? And so what Newton's law says is that this is equal to the sum of the forces, external forces acting on that object. Okay? And so the way we can express this mathematically, okay, the time rate of change is going to be d dt. Momentum is going to be mass times velocity, okay? And this is equal to the sum of all the forces, okay? And so if we carry this time derivative throughout, usually we assume that mass is constant. So we have m dv dt, okay? Which dv dt we know is just acceleration. So we have ma is equal to f, right? And so this is just Newton's second law. So this is just another way of saying F is equal to ma, where F is equal to ma is just another way to say the rate at which linear momentum is changing on an object is equal to the sum of the forces. So if you push an object, its momentum is going to change. If you kind of try to stop an object coming towards you, you're applying a force to change the momentum of an object. Okay, and so we can kind of take this idea into fluid mechanics, right? So particular, if we think about kind of our three big terms for Reynolds transport. So Reynolds transport, remember we had our production term, or our generation term, we had our accumulation term, and then we also had our inflow outflow term, okay? And I want to just kind of focus on just one term right now, which is the production generation term, okay? And so remember our production generation term looks like this. So is our big derivative, okay? Right. And so in this particular case, since we're applying this to conservation momentum, we're going to set big B equal to momentum. Okay, so big B is just going to be mass times velocity. Okay. And so what we're saying is that big D, big T of mass times velocity is equal to the sum of all the forces. Or in other words, one way that we can say this is that one way that we can produce or generate momentum in a fluid is by applying an external force on it. So if we want to say we have a fluid that's, you know, still inside a glass like this. Okay, one way that we can speed it up, we can give it velocity, is we can apply an external force, right? So if I took this glass of water and poured it all over my laptop, you know, we have an external force of gravity that's acting on the fluid, right? So that external force of gravity is going to work to accelerate that fluid towards my laptop, ruin my entire life, and then you know, I'd have to buy a new laptop for next week. So I'm not going to show an in-class demo of that, but you can kind of imagine what that would be like in your heads. Okay. And so this is, you know, this is going to be expressly different than, you know, what we did for conservation of mass, right? So conservation of mass, when we took our production term, we said that there's no way for us to generate kind of mass out of nothing, right? So whenever we express RTT for mass, we just set that production term equal to 0. Okay, and so that's going to be different here in momentum. So our production term here is going to be the sum of all the forces acting on an object. Okay, and a lot of times for these problems, what we're going to be solving for is exactly those forces. Okay, so we'll do an example of, like, say we have like a hose hitting like a wall or something, right? And so in order for the wall to kind of stay anchored, there has to be kind of a reaction force from that wall. And so through this conservation of linear momentum with Reynolds transport, we'll be able to solve for what is that kind of reaction force in the wall. Okay. Okay. And then one last note before I turn the page. So remember, you know, when we're doing Reynolds transport, we have this difference between big B, which is our extensive property, and little b, which is our intensive property. And the way we get little b is we just take big B divided by m. And so big B is equal to mass times velocity. Little b is just equal to velocity. Okay. Okay. Any questions on this page? Okay. Okay, so let's write out the Reynolds transport expression for conservation of momentum. Okay? And so on the left-hand side of the equal sign, we have the sum of the external forces, right? Just like we said. Okay, so this is going to be equal to our accumulation terms. We have partial t of integral over the control volume of u rho dv. Okay. Okay. Plus our inflow outflow term. Okay. So that's the integral over the control surface of u rho u hat dot n dA. Okay. Right. And just to label this is right here production and momentum. This right here is accumulation. Okay. And this last term right here, this is inflow outflow. Okay. And so you can see, you know, there, it looks pretty similar to our conservation of mass RTT, but with some key differences, right? And so we have some extra velocities that are kind of floating around here, because remember our little b is velocity. And of course, our production term here is the sum of the forces, okay? Right? These look like kind of subtle differences, but there's kind of one really big key thing that that's going to be big difference here. Okay? And that's due to the fact that forces, both the forces and the velocities that I've circled here, all of these are vector quantities. And so just by virtue of being a vector quantity, it has components in the x. Well, mostly we're going to do 2D problems. It's going to have components in the x and the y directions. Okay. Okay. And so when you're doing these conservation momentum problems, a lot of times you have to apply this RTT in the x direction, and then you have to apply it again in the y direction, and then your forces and your velocities are going to be different there too. So I want you guys to kind of keep that in mind. Okay. Okay. And so another thing I want to kind of to state is that even though this is kind of the full form of RTT for momentum, you know, for most of the problems we're going to do in this class, I say most, but it's actually all of them. So we're only going to consider steady situations. Okay. Okay. And the reason for that is this guy right here. So it's our accumulation term. Okay. And so if basically if our situation was unsteady, we would say that our control volume is accumulating momentum as a function of time. Okay. And if that's the case, and our momentum is in our control volume is accumulating momentum, then you know the only way for that to happen is if our control volume is accelerating or decelerating. Okay. Okay. And so once you, if you do have a case where they're accelerating or decelerating, that actually complicates the math quite a bit, and we actually have to add some additional terms to account for that acceleration. So that's beyond the scope of this class. So that's more kind of a graduate level fluid mechanics topic. So we're not going to cover those things. So we're only going to be covering kind of steady situations where either the control volume is fixed in space or it's moving at some constant velocity. You know, and those are basically the only two cases that we can do. Okay, and so just like I mentioned on the previous page, you know, a lot of times what we're interested in is the forces, these forces right here, okay? And so a lot of times in these problems, you know, what we're going to be solving for are the external forces, and these external forces can have some kind of these kinds of effects on fluids. Okay? So in other words, you know, these external forces that we're going to be solving for, it can either cause a fluid to speed up, okay? It can cause a fluid to slow down, okay? So it can these are basically just changes in velocity, at least in the magnitude, okay? And in another case, it can cause it to change directions as well. And so whenever you come across a fluids problem where you see, you know, the fluid is either accelerating as it goes, or it slows down, or you know it changes direction, you know, there has to be some kind of external forces that are being applied in those cases. Okay, and a lot of times what we're interested in is solving for these external forces, and this RTT expression gives us the tools to do that. Okay. Okay. Any questions on this? Question. So for the CS term in the above, is it U minus N? No, it's a U dot N. Yeah, remember this is our dot product right here. Yeah. Mm-hmm. Okay. Okay. So what are so before we do an example, I also just want to mention, you know, what are the kind of the typical types of forces that can cause these changes. And so these are typical. So of course, you know, there's more forces than these, but you know, for most of the things in the class, this is what we're going to be dealing with. So first of all, we have pressure, right? And so we kind of already know this from Bernoulli, right? So we know that pressure and velocity kind of have this relationship where if you have a difference in pressure in a flow, you have a high inlet pressure, a low outlet pressure, that's going to cause the flow to kind of move in that direction. Okay. So that we've seen from Bernoulli already. Okay. And so the next is friction. Okay. And so fluids are subject to friction too. And kind of the main driving force for friction is actually viscosity. Okay. And so another quantity is the weight. Okay. And so just like I talked about earlier, where you're pouring water out of a glass, that's gravity forces that can accelerate a fluid. Okay. Okay. And then the last category of forces are reaction forces. Okay. So a lot of times, when you have a fluid flow, it's going to either strike a solid object or it's going to be guided by a solid object to change direction. Okay. And so there are going to be reaction forces that come from that object that are going to be placed on the fluid. That's either going to cause it to speed up, slow down, or change direction. Okay? And a lot of times these are the kind of the categories of forces that we're going to be solving for. Okay, as will be illustrated in the next example. Okay. Okay, and so let's do an example. Okay. And so let's say that we have a jet of water and it's kind of striking this this ramp thing. Okay, and so we have a ramp, let's say it looks like this. Okay, this ramp is anchored to the ground. Okay, and then at this ramp, we're going to basically shoot a hose of water. And so it's going to follow the ramp and going to look like that. Okay. And so we know some statistics about this. So we can say that at the inlet right here, we have an inlet velocity of 10 feet per second. Okay. And then we also know the angle at which this flow is coming out. Okay. And there has to be a U2. Okay. And so another thing that we know is that A1, or the area that's for the inlet jet, is going to be equal to the area of the outlet jet too. Okay. All right. And so what we're interested in solving for is basically what are the forces that are required to keep this ramp in place. Okay. Okay. And so before we start, because this is a control volume problem, we need to draw our control volume. Okay. So let me go ahead and do that. So here it's fairly straightforward. We're just going to draw a control volume around the ramp. Okay. All right. But this is kind of the first time that we're going to start to apply some of those control volume rules that we talked about maybe a couple of weeks ago. Okay? And in particular, I want to draw your attention to this area over here. Okay? And so if you notice in this area right here, I've drawn the control volume surface to be kind of at an angle like this. Okay. Okay. And the reason I did that was so that the control volume surface will be perpendicular to the flow velocity coming out right there. Okay. And if you remember, we want to do this so that when we compute our dot product u dot n, we just get a whole number and we don't have to worry about any angles like that. Okay. And so if we do this here, then the normal vector to that surface will be just like this. And then in this particular case, the flow velocity vector will look like that as well. So they're parallel to each other. Okay. And then same thing right here. So here the normal vector is pointing that way, and then the flow velocity is pointing in, just like that. Okay. So we want these to be parallel to each other, just so that we don't have to apply any angles to our dot product. We just kind of multiply their magnitudes, and then just either make it positive or negative, depending if it's an inflow or an outflow. Okay. All right. Any questions on the problem setup? Okay. Okay, so let's start solving this problem. So even though, we're solving for the anchoring forces right here, usually when you do conservation of momentum problems, first thing you should do is you should do conservation of mass. Okay. And the reason you wanted to start with conservation of mass is that conservation of mass will usually allow you to solve for all the velocities in the system. Okay. And so in this problem, we do have one unknown velocity, and that unknown velocity here is u2, which is the outlet velocity. Okay. And so we know that u1 is equal to 10 feet per second, but before we even start to go on with momentum, we need to solve for u2. Okay. And so in this problem, it might be kind of obvious what u2 is, but I just kind of want to show you the full process here, just to kind of show you, what to do for kind of more complicated problems. Okay. And so let's apply our conservation of mass. Okay, so conservation of mass, we have 0 is equal to partial t of rho dv, okay, plus, let's see. Okay, so there's our conservation of mass. And so first we're going to cross out this first term because it's steady. Okay. And then we'll replace this with kind of our usual expression for this, which is m dot out minus m dot in. Okay. Okay, so we have 0 is equal to m dot out minus m dot in. Okay. And so what this is saying is that the mass flow rate out has to equal mass flow rate in. Okay. And so if we plug in the expression for the mass flow rate, which is density times area times velocity, okay, we see that the densities here are going to cancel out. Okay. We also know from the problem that since A2 is equal to A1, okay, so that was given to us in the problem, we can cancel out the areas. Okay. And we can solve for U2, which is just going to be the exact same as U1, which is 10 feet per second. Okay. Okay. Right. Any questions on that? Okay. And so, one thing I'll comment on before we move forward is atmospheric pressures. Okay. And so, it's kind of implied from this problem that this ramp is kind of just in the ambient air. Okay. And so the atmospheric pressure is kind of the same all around this. Okay. And so the reason I make that comment is you could have situations where you have an imbalance of pressure. Okay? So this is not going to be the case here, but you're going to come across situations where, say that the inlet has some pressure P1 and the outlet has some pressure P2. Okay. And so what that basically means is that any imbalance in pressure can cause a force on a system. Okay. And so this is mostly relevant for either for flows in an airplane engine or flows in a pipe, actually. Okay? And so we don't have that in this case. So in this case, we have the same pressure at the inlet and outlet, and so there's going to be there's no net pressure force. Okay? but I want you guys to just kind of be aware of it, where like if you're going to look at some examples in the book, or you're doing some practice problems in the end of the chapter, you know, if they give you a pressure value, you know, this is why that is. Okay, and we know how to compute force from pressure, right? So if you have some kind of pressure, so P1, the way that you get force from this is just equal P1 times the area, right? And so those are kind of additional forces that you can have in these problems. So so again, you know, that's not the case here, but if you do come across these later on, I think we're going to do an example of this later. You know, this is what you would do, but I just kind of want to mention it right now because you know, sometimes the question is asked, you know, what happens with atmospheric pressure? Okay. Any questions on this? Okay. All right, so now that we've applied conservation of mass and we know that U2 is equal to U1, we're ready to apply RTT for momentum. Okay. Okay. And so RTT for momentum, you know, we want to be able to solve for the forces that are acting on the vane, basically, or on the ramp. Okay. And so remember, momentum is a vector, and so we need to basically apply this in both the x direction and the y direction. Okay. So let's do x first. Okay. So from the x direction, we have sum of all the forces in the x direction is going to be equal to partial t of u rho dv, okay, plus integral of the control surface of u rho u vector dot n hat dA. Okay, so that's the x direction, and now let's do the y. Okay. Okay. And so in the y direction, we have sum of all the forces in the y direction is equal to partial t of the integral of rho times v. And so little v right here is the y component velocity plus integral of v rho u dot n hat dA. Okay. All right. So there's a lot going on here. So let's kind of break it down kind of step by step. Okay. So first of all, let's look at these unsteady terms. Let's look at them and then just kind of wave goodbye, okay? Because remember, you know, for these momentum problems, most of the time we're going to be looking at steady problems, okay? Okay. So we can let these unsteady terms, you know, go on vacation in Cancun, just like the LA Clippers are doing probably right now. Okay. Okay. And so let's now look at these guys. Okay. There's a lot of subtlety in these integral expressions right here. So let's kind of break it apart kind of step by step. Okay. So first thing I want you to look at are these velocities right here. Okay. And so notice for these velocities, I didn't draw an arrow on top. Okay. And that's by design. Okay. So these velocities in blue and so these velocities are called, I give them the name component velocities. Okay. Or momentum velocities. Okay. Okay. And so the reason I give them these names is because these are the actual components of velocity, right? And so, you know, if we write out our velocity vector, it looks, in 2D, it looks something like this, right? So our velocity vector is comprised of the x component velocity, which is little u, and then the y component of the velocity, which is little v, okay? And so these velocities that I boxed in blue are exactly those velocities. And so the most important thing is that these velocities here, these follow the Cartesian sign convention. Okay. okay? And so these, for these velocities, you're going to plug in a positive if it's going to the right, a negative if it's going to the left, positive if it's going up, negative if it's going down, okay? And the other important thing is that, is to remember that these are the components. And so if we have a situation which we have here where the velocity is going at an angle, you're going to plug in, you have a velocity that's going at an angle like this. For the x component of the momentum, you're only going to plug in the x component of velocity here, okay? Okay. And so that says components at the end, so let me rewrite that. Okay. And so, if we have a velocity that goes like this, okay, so maybe this has velocity magnitude of u bar like that, okay, and there's an angle. And so if we break this up into components, you'd have u cosine theta for the x component, okay, and then for the y component, we would have u sine theta, okay. Right, and then we would actually plug in these components right here into that integral expression up there. So I'll show you kind of how this is, but I want you guys to remember that that first velocity right there is the component velocity or the momentum, okay? And so these velocities, they follow the Cartesian sign convention, and they have to be the actual components of velocity. So if you have a velocity at an angle, you have to actually break it up into the x component and the y component, and then plug them into the respective parts of the momentum equation, okay?
Professor, you're taking the absolute value, or you're taking the magnitude?
That's the magnitude. Yeah. Yeah. Okay. Any questions on this before I go over the orange box velocity?
So we just take the scalar amount of it?
Yes. So you're going to take the scalar amount of the component, and then you're going to set it to positive or negative depending on which Cartesian direction it's going. Yeah.
Is that because we're already taking consideration the velocity when we're doing the dot product to the normal vector?
Yeah. So we're going to go over that next, and that velocity right there is in the orange is actually going to respect the inflow outflow stuff that we talked about. Yeah. Mm-hmm. Okay, so let's go over the orange box velocities. And so the name that I give these velocities is the convective or the carrying velocity. Okay. Okay. And so these guys, these follow the usual inflow-outflow sign convention. Because remember, it's dot product with the normal vector. Okay. And for these ones, if you draw your control volume right, the way that you're going to the thing that you're going to plug in is not the components of velocity, but just the magnitude of the velocity itself. Okay. Okay. And so the reason I call this the carrying velocity is, remember this expression that we're going over, Reynolds transport theorem. The key part of that is transport, right? And so what Reynolds transport theorem expresses is how certain quantities are transported through a control volume through a fluid. Okay? And so in order to transport things, they have to kind of be riding along with the fluid. Okay? And so what this carrying velocity expresses is how certain quantities are carried through a control volume. Okay. And so if you think about it, we had this U dot N term for our conservation of mass, right? So in conservation of mass, this U dot N expressed how mass was carried through our system, okay? And so that's kind of a pretty intuitive thing. But in this particular case for momentum, momentum can also be carried into our system and also be carried out through our system. So it's kind of a weird concept to think about, momentum being carried through something, because you can't, pick up a bundle of momentum and, carry it across, into the wilderness or something like that. But, for fluids have this very unique thing, because it has momentum, but the momentum can kind of carry momentum itself into and out of certain places. So it's a very weird way of thinking about it, but I think once you kind of say it kind of a few more times, it starts to make a bit more sense. And that's what this expression basically is. Okay? And so this product of the momentum velocity here and the carrying velocity right here, that expresses how momentum can be carried through a system. Okay. And so let's kind of put this all together. Okay. And so let's basically apply this. Okay. Let's apply this on our ramp, and then we're going to apply it basically 4 different times. So we're going to do the X component at the inlet, the Y component at the inlet, and then we're going to do the X component at the outlet, and then the Y component at the outlet. So we're going to do this 4 times, okay? Okay. And so let's do the inlet first. Okay. And so for the inlet, let's do the X direction first. Okay. And so let's write out our integral expression. So our integral expression here is integral of U rho U dot N dA. Okay. And so let's start with the, let's start with simply rho and A. Okay. Okay. Because we have the density that's going to come out, and then we have the area that's going to come out. Now let's start with the component velocity, right? So our component velocity at the inlet, we have we have a fluid velocity that's going to the right here, okay, and has a magnitude of U1, okay. And so since it's going to the right, the momentum velocity that we're going to plug in is a positive U1, okay. Right. And then for the carrying velocity, we're going to input the magnitude of this velocity, which is U1 as well, okay? But, for the carrying velocity, we're going to respect the inflow-outflow conventions. And since this is an inflow, we're going to put a negative right there, okay? And so we have a positive U1 for the momentum velocity and a minus U1 for the carrying velocity, okay? Right, so that's the X component. So now let's do the Y component. Okay, and so for the Y component, we have density times area, okay, just like we did before. Next, let's write the component velocity, right? And so now let's ask, what's the Y component of the velocity at the inlet, right? At the inlet, we have a velocity that's purely horizontal, okay, so there's no vertical component at all. And so for the Y component, we're just going to put 0, okay? And then our carrying velocities here are going to be the same, because for the carrying velocity, we have the magnitude of the velocity, which is U1, okay? And we have a minus U1 because it's the inlet, okay? All right. Does that kind of make sense how we specified these velocities here?
Can you repeat again why the U1 is 0 in this case?
Right. So in this case, the 0 comes from the fact that this expression right here, this is the Y component of the momentum at the inlet. And so since at the inlet over here, the inlet, we have just a horizontal velocity, right? Okay. So there's no Y component there. So for the component velocity, we input 0. Yeah, so there's lots of different sign conventions and lots of different components going on. So definitely take your time with these problems. You know, that's kind of why I'm really kind of taking the time with this example too, just to kind of explain kind of every kind of little subtlety and every kind of little intricacy, because there's a lot to kind of keep in mind. Okay. So that's the inlet. So now let's do the same thing for the outlet. Okay. So remember, our outlet is angled kind of upwards at an angle. Okay. So that's going to affect our components. Okay. And so let's do the x direction first. And so at the outlet, for the x direction, we have rho times u dot n dA. Okay. And so first, let's write rho and a. Okay. So we have rho a2. Okay. Remember, our outlet has a velocity stream that looks like this, right? So it's an angle theta. And so the x component of that is going to be u2 cosine of theta. Okay. And then our carrying velocity, remember, we're just going to take the magnitude of this velocity stream, which is u2, and then since it's an outlet, we're going to make it a positive u2. Okay. Okay. And then finally, we can do the y component. So in the y component, we have rho a2. Okay. Our component velocity is going to be u2 sine theta. Okay. And then our carrying velocity here is just going to be u2. Okay. All right. Okay. And so now that we've solved for the x and y coordinates, x and y components in the x and the y direction, or at the inlets and the outlets, let's sum them up together. Okay. And so we can say that the sum of the forces in the x direction is going to be the sum of this and also from this. Okay. And so let's write the contribution from the inlet first. So at the inlet, we have a minus rho a1 u1 squared. Okay. And so remember, this is coming from the inlet. Okay. And then for the outlet, we have the quantity that's up there. Okay. So we have rho a2 u2 squared cosine theta. Okay. This is from the outlet. Okay, and the sum of the forces in the y direction, we have 0 that's coming from the inlet, okay, plus rho a2 u2 squared sine theta, okay. And so this again is the inlet, and this is the outlet, okay. All right. And so you put it all together, and we can say that the reaction force in the x direction is equal to minus, since everything is variables here, we can just say that this is equal to just fx, and this is equal to fy. Okay? And so this top expression right here is the reaction force in the x direction from the ramp, and this expression right here is the reaction force from the ramp in the y direction. Okay. All right, any questions on this example here?
Explain again the sign convention for the carrying velocities that you're making positive and negative for outflow and inflow.
Right, so the carrying velocities here are in the orange ones. And so for the carrying velocities, we make it positive if the flow is at an outlet, and we make it negative if the flow is at an inlet. And so, for the outlet, I'm basically considering this flow that's up here, right here, okay? And so since at the outlet, we have the dot product between the velocity and the normal vectors of the surface. So since they're in the same direction, we make it a positive number, okay? But at the inlet, they're going in the opposite direction. So you have, the flow that's going in this way, and then the normal vector is going this way. So you take the dot product between them, you get a negative number because they're anti-parallel to each other.
And would that be the same for every problem, or is that going to be very specific?
That's for every problem. So every problem, if you're basically going to evaluate this this integral right here. These integrals on the right here, you're going to be evaluating them at every inlet and outlet of your model. So if you're doing it for an inlet, you do a negative carrying velocity, and for an outlet, you do a positive carrying velocity.
Okay, thank you.
Yep. All right, question: are the orange velocities just for direction? Is that why the y component velocity is 0? The blue velocities are for the components, for the directions. And so the orange ones, remember, you just do the magnitude and just do positive or negative if it's inlet or outlet. Yeah. All right. Okay. And so there's one more example in the notes that considers an airplane turbine. But I want to make sure I do the example with the moving control volume, just because I know these can get really tricky, and we only have about 20 more minutes left. Okay.
Professor, for the previous problem, so what we solved for was a quantity, the reaction forces at what point of the ramp, like at the centroid, or?
Yeah, that's a great question. So it's you can kind of think of these forces as kind of acting throughout the fluid, right? Because we know that forces are required in this case, the force is required to basically change the direction of this flow, right? So it went from purely horizontal to vertical. And so those forces you can kind of think as acting on the fluid, kind of just like this. And so, in reality, these are the forces that are acting on the entire control volume, like this, okay? But you can kind of think of them as forces that are acting on the fluid itself. And these are just kind of the resultant or the overall forces from that.
Thank you.
Mm-hmm.
So you're skipping the turbine example and going to the moving control volume?
Yeah, because it's because I want to make sure I do the moving control volume one, because there's even more going on there with the velocities. But the turbine one I think is not too difficult. So I think if you kind of read through it and kind of follow the same process that we did, it should be pretty self-explanatory from there. That one's even easier because everything just kind of goes in one. Okay, and so now we're going to consider basically momentum problems where the control volume is actually moving. So, it's another layer of complexity, and you have kind of a ton of velocities going through. Okay? And so remember, for moving control volumes, we're going to use this W vector right here, which is the relative velocity. Okay? And the relative velocity is going to be V, or U, I would say. So U, which is the fluid velocity, minus velocity of the control volume. Okay? And we're going to replace our carrying velocities with these. So we're not going to replace the component velocities. We're just going to replace the carrying velocities. Okay? Okay. And so our expression is going to look like this. So it's going to look like partial t, okay? Integral of u rho dv, okay? And so remember that's just the regular component u, and so we're not replacing that. And it's going to this we're going to add our inflow outflow term. Okay. And you can see the only adjustment that we made was in this term right here, where we replaced the carrying velocity with the relative velocity. Okay. And so that's one form of conservation momentum with the moving control volume. But sometimes it's actually more convenient to put everything in terms of W. Okay. Okay. And so we're basically going to replace all of our U's with W plus VCV. Okay. Because if we kind of rearrange this expression right here, we can solve for U hat and or U vector, and U vector is just going to be W plus VCV. Okay. And so if we write all that in, we have partial T of integral of W plus VCV, okay, rho d volume, okay, plus integral over the control surface of W plus VCV, okay, W dot N dA, okay. And so both of these forms are valid. It's just that sometimes the bottom one is a little bit more convenient because, you know, we're going to be computing the relative velocity anyway. Okay. Okay. So let's do. And so if we do like what we usually do, we assume that this is steady. Okay. Okay. Let's distribute this guy and break it up into two components or two terms. Okay. All right. Before I do that, are there any questions on this page? Okay. Okay, so if we distribute that and kind of break it up into two terms, we'll have one term which is kind of the, you know, it just has the relative velocities, and we'll have another term which has the VCV. Okay, and so what we get is, remember we've already canceled out the unsteady term. Okay. Okay, first we have that, then we have VCV. Okay, so VCV here is, you know, it doesn't change depending on area, and so we can kind of think of it as just a constant. Okay, and so we can pull that out of the integral, and then what we get is integral of rho W dot N dA is equal to the sum of all the forces. Okay. Okay. And so we can actually simplify this quite a bit more, okay? Because if we look at this guy right here, right? So this guy is just integral of rho W dot N, okay, dA. Okay. This guy should look familiar because this guy is basically our inflow-outflow term without the velocity, okay? And so this is actually our inflow-outflow term from conservation of mass. Okay. And so we can actually, you know, we can actually set this term equal to 0 because we know that we're in a steady situation. And so in a steady situation, we know that the, you know, mass cannot accumulate or decrease in the control volume. And so because of that, you know, the inflow of mass and the outflow of mass for the entire control volume has to be the same. Okay? And so when we perform this integral, this is actually 0, okay? Because steady. Okay? And so that simplifies our expression quite a bit. And so we can get the following expression for the conservation of momentum for a moving control volume. Okay? And so we're all just left with this guy right here. So we have the integral of W rho times W dot N dA is equal to the sum of all the forces. Okay. And so this right here is conservation of momentum for moving control volume. Okay. And so even though, you know, we have everything in terms of relative velocities here, I want you guys to kind of to still remember the interpretations for each of these velocities. Okay. And so first in the blue right here, we have our momentum velocities or component velocities. Okay. And so just because it's a relative velocity, that's not going to change. Okay. And next, in the orange right here, these are our carrying velocities. Okay. Okay. And so these are going to follow all the same rules as you know, our previous problems or the previous example that we did, except now it's going to be relative stuff because it's a moving control volume. Okay. All right. Any questions on this? Okay. And so let's do an example with the moving control volume. Okay. And so we're going to do our exact same ramp that we did before, except now we're going to give it wheels. Okay? Just like every good fairy princess castle should have wheels. Okay. So there's our ramp. It has wheels. Okay. And it looks like a really weird roller blade. Okay. And then because of the water that's striking it, we can say that that our cart here is going to be moving forward with the velocity 20 feet per second. Okay. It's really fast, actually. What the heck? Okay. And so we have a stream of water that's hitting it. Okay. And so we know that V1 right here is going to be 100 feet per second. Okay. We know that A1 is going to be 0.00 0.006 feet squared. Okay. And we know the angle here, so the angle here is going to be 45 degrees. Okay. And the density is 1.94 slugs per feet cubed. Okay. Slugs is one of the units of mass in the English units. Okay. And so just like before, we're going to draw our control volume. Okay. And then from this problem, what we want to do is we want to solve for the magnitude and the direction of the force exerted of the reaction force, basically. Okay. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and start solving the problem. So first thing that we need to do is that you know, we need to solve for our relative velocity because it's a moving control volume problem. Okay. Okay. And at the same time, we're going to apply conservation of mass. Okay. Okay. And so, you know, the first thing that we can do is that, you know, we know the velocity of the water at the inlet, right? Okay. So we know the velocity at the inlet is going to be 100 feet per second, but we also know that the control volume is moving in the same direction at 20 feet per second. Okay? And so let's compute W1. Okay, and so W1 is just going to be the fluid velocity U1 minus velocity of the control volume, which is V naught. Okay, and so in this case, they're both going in the same direction, so they're both going to be positive here. Okay, so we don't have to change any signs. And so we do 100 minus 20, and we get 80 feet per second. Okay, so that's W1. And so the next thing that we'll compute is W2 at the outlet. Okay. And so since we have a steady problem, we know that we have this. Okay. So this is for conservation of mass. Okay. And so if we actually work through the math right here, we can see that W2 is going to equal to W1. Okay. And so W2 will also equal 80 feet per second. Okay.
Is that a 8 or a 0?
Which one? Oh, this is a 0. Sorry. Okay. Okay. And so we have a relative velocity of 80 feet per second at the inlet, and in order for us to satisfy conservation of mass, the magnitude of the outlet jet also has to be 80 feet per second. Okay. All right. Any questions on that? Okay. And so now that we have this, we can apply conservation momentum in the X and Y directions. Okay. And so first, let's do in the X direction. Okay. And so I'm going to do the X component, the X direction for the inlet and the outlet. Okay. And so Fx is going to be W rho W dot N dA. Okay. And so first, let's do the inlet. And so at the inlet, we're going to have rho A1. Okay. And then we're going to multiply this by the X component of the relative velocity at the inlet. Okay. So let me use the same color scheme that I've used before. And so the X component at the inlet is just going to be a positive W1. Okay. Because remember that at the inlet, we have velocity going to the right like this. Okay. So that's going to be a positive W1. Okay. And then our carrying velocity here will be also have a magnitude of W1, but it's going to be negative because it's at the inlet, right? And so this expression right here is for the inlet. Okay. And then to this, we're going to add the expression at the outlet. Okay. And so the outlet, we have a rho. Well, we say the outlet velocity is the same as the inlet, or the outlet area is the same as the inlet. Okay. And so first, let's do the component. And so the component velocity we know is going to, since our outlet here is angled, is going to be at an angle. So we have W1 cosine theta. Okay. And then our carrying velocity here will be a positive W1 because it's at the outlet. Okay. And so this is for the outlet here. Okay. And so if we plug in all the numbers, you plug in all the values for this, we get the force in the X direction is equal to minus 21.2, or positive 21.2, sorry, positive 21.2 pounds. Okay. All right. And so now let's do the same in the Y direction. Okay. Okay. So Fy will be, the same thing. And so at the inlet, our inlet is totally horizontal, so we have just a 0 velocity there. Okay. So that's the component. For the carrying velocity, we're going to have a minus W1. Okay. And for the outlet, we're going to have rho A1. Our y component is going to be W1 sine theta. Okay. And then our carrying velocity here will just be a positive W1. Okay. And so if we plug in the numbers for this, we get Fy is equal to minus, positive 52 pounds, 52.6. Okay. And actually, this is a minus 21 right here. Okay. 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 And so these forces right here are the velocities that the ramp imparts on the fluid. Okay. Okay. And so in order to get the magnitude, we can just take, we just use the Pythagorean theorem. Okay. And so the magnitude here is going to be 57.3 pounds. Okay. And then direction, we just take the arctan of these angles. Okay. So you have 52.6 divided by minus 21.2. Okay. And this is going to be a positive 68.05 degrees. Okay. So this is a little bit different from the one that's in the notes, because in the notes I did kind of the opposite of these forces. Okay. But I think we'll talk about that next time about why I did that. Because I went a little bit over time today, so I apologize for that. And so I'll get you guys your comments on the midterm exam. So I'll see if I can activate a setting on Canvas. If not, then I'll email them to you. But if not, thank you guys for tuning in today. So there's a midterm. I mean, there's a new minute paper on the Canvas site up right now. It's different from the previous minute papers. So it's this one is kind of like a midpoint checkup. And so what I want you guys to just talk about is, how the class is going for you at this midpoint, how you feel about the class, and if there's anything that you want to see from me going forward to kind of improve the class, we go from there. Okay. But besides that, thank you guys for tuning in. I apologize for going over time a little bit. Have a great weekend, and I'll see you guys on Monday.
All right. Thanks, Professor. Hope you enjoy your weekend as well.
Yep. You too.
Over for office hours?
There's no office hours today, but I'll stick around if you guys have any more questions right now.
Oh, I just had a few questions concerning my grade, that is all.
Okay. Yeah, if you want to talk about it, I do have something to do at 10 o'clock today, but if you want to send me an email, we can set up a Zoom meeting to chat about it.
Okay, thank you.
Yep. Mm-hmm.
Did you put minute papers in our week 7?
It's on the quiz. So if you go to quizzes under the campus site, yeah, that's a good idea. I should actually put it in the weekly thing, just so it's easier to find, I think.
Yeah, no, I mean, I think I knew that they were there, but I should have thought about it. Thanks.
Yeah.